Hello, in this video we're going to be seeing how we can use the Python programming language in order to visualize filters. So here on the left I have an image of a cat, and on the right I have the same image, but I'm progressively showing a filter being applied. In this particular case we're using convolution to do the filtering. And as we can see, in this particular case the filter is a 3x3 edge detection filter. So what does that mean? Well, if we go to the Wikipedia page for digital image processing, we can scroll down and we get a section digital image transformations. And under filtering, it's said that digital filters are used to blur and sharpen digital images, and filtering can be performed in two ways: convolution and masking. So convolution works in the spatial domain, so on the image itself, and masking works in the Fourier domain, so in the discrete Fourier transform domain. What actually happens when filtering? So if you look here, click on the kernels, if you scroll down, we get the formula. So this is just the formula for the convolution. So every pixel in the image is made up from some weighted sum of its neighboring pixels. So in this particular case, for the identity operator, every single pixel would be the one in the middle, is made up of a weighted sum of the middle pixel and all its immediate neighbours with an amplitude of 0. So it truly is the identity is that the resulting filtered image would just be the original image. We then go down and see more interesting examples. So for example, the edge detection filters. So again, it's saying that every single pixel on the original image is some sum of its neighbouring pixels. For this particular case, it's 1 times the pixel to the top left, minus 1 times the pixel to the top right, minus 1 times the pixel to the bottom left, and minus 1 times the pixel to the bottom right. And what that leaves you with is an image in which the edge has been detected. So this kernel here is basically saying only when there is a change between pixels, amplify that difference between the pixels and store that as the filtered image. There are some more complicated examples, especially with larger kernels, in which the weighted sum applies to more of the pixels around it. But for this example, we're just going to be using 3x3 kernels. So the first thing we're going to do is we need to import some things. So as usual, we're going to import NumPy for all the numerical stuff, SciPy for all the scientific stuff, itertools, some iteration things, and then matplotlib along with the matplotlib animation library so we can animate the plot. I'm going to give it a default plot size of 14 inch by 7, make it nice and big. And so the first thing we need to do is we need to load in an image. So luckily I have an image prepared, which is an image of a cat. So we'll go ahead and read in the cat image. Which is loaded in here on the right as an array of unsigned bytes. So it's a 512, 512 by 3 array with the last index being the colour RGB. What we're going to then do is we can actually cheat. We don't actually need to perform the convolution on each individual pixel and plot how that convolution changes in time. What we can do is we can just use the SciPy built-in function convolution and create the filtered image with our desired kernel, and then simply plot that over the original image. So I'm going to load in a couple of kernels. So we're going to have 2 kernels here. We're going to have an edge detection 3x3, which is given by -1, -1, -1, -1, 8, -1, -1, -1, -1, and a sharpen 3x3 filter. And we'll see how both of those work. We'll choose a kernel. We're going to create a function to do the convolution because we need to do the convolution on both the red, green and blue channels individually. So we'll create an array im2, we'll create an array image2, which will be empty but will have the same shape and data type as image1, which is the image going in. We're going to be using the function convol2d, which is from the scipy.signal library. So we'll be convolving the input image with the kernel and using the same size array on the output, and at the boundary doing symmetry. So on the boundary it basically acts like a mirror. So let's go ahead and test that. We won't actually know if that's done anything yet. So what we need to do now is actually plot it. So to plot it we use image show. Plot the data on the left and the filtered image on the right for now, just to check it. Go ahead and plot that. You see we get exactly what we want. So on the left is our original image of the cat, and on the right is our edge detection image. But you see we have a slight problem. The image on the right doesn't look right, as it were. And that's because when we loaded in the image using imread, it created an array of bytes, and so bytes can't take values in between. And likewise, it can't store a value greater than 255. So it can store anywhere between 0 and 255. And so this ends up being clipped heavily. So what we're seeing is only a small portion of the actual resulting filter. So we can go ahead and sort that out. So let's try doing something like this. Let's simply try casting it to a float. And now that does look better. But on the left, we're not getting anything now, because we're now no longer have byte values, so integer values for our image. Matplotlib has recognised that it's a float, so it's expecting a value between 0 and 1, not 0 and 255. So we need to go ahead and rescale it. We plot that now, we get something a lot nicer. So we have exactly what we expect. So we have a picture of the cat on the left, and then the edge detection image on the right, with the full values going roughly from complete black to complete white from the image. Good. Now what we need to do is we need to be able to figure out some way of making sure we can overlap the two images. And I think a really neat way of doing this is to add an alpha channel. So because when we read in a PNG, when we read in a JPEG, it doesn't include an alpha channel, but we can go ahead and add an alpha channel to our image. The first thing we need to do is we need to shield this. So if we load in a PNG, for example, or another image format that's including an alpha channel, we need to ignore it. So we force the shape to be width times height times 4 now, so RGB alpha. Then we need to make sure that the new image that we've just created has the same RGB components. So this function by default will add an alpha channel to our RGB array with the value of 1, so not transparent, so fully visible. Go ahead and try that. Okay, so the image on the left still works, but now we've broken the filtered image on the right. And that's because we had no guard in this function here to say what happens when there is an alpha channel. So we only want to do the convolution on the RGB channels, not the RGBA. Got that, we'll do numpy.copy image 1 in the original function, so it takes all values, and then we override the RGB channels. That gives us back our original image. But now, in our filtered image, we now have a fourth channel, which is the RGB, which is the alpha channel, currently set to 1. So we can go ahead and use that now, because if we set the alpha channel to 0, it becomes invisible. So we'll plot it. Let's create a third matrix called im_display. It'll be a copy of the original data. We'll then go ahead and plot this. To visit. And the cat has come to visit. And actually I've just thought of a better way of doing this without using the alpha channel. But we can keep the alpha channel stuff in because that'll be useful if we load in an image with an alpha channel. To create our image display, which is just at the minute copy of the original image. Go ahead and create an animation. So we'll be using blitzing in order to speed up the plot. And we need to tell it how to create a new blank plot. So we'll tell it that to create a blank plot, it can just show the original image on the right hand side. We need a handle to each of our images. And then we need a function that tells it what to do in order to update the plot. And it will receive frames, so the current frame number, which we can change. The most essential thing we're going to want to do is we're definitely going to want to set the image on the right to the display data, and then we're going to change the display data in this function. We then need to tell it that the image on the right has changed because we'll be enable blitzing. Just copy over the function animation code. Then you see that we need this FPS. So we're going to select how many frames per second to plot. You can put that near the top. 30 FPS. We also want some way of actually looping across the indices. So the easiest way to do that is to use iter tools, which we import at the top as it.product. And then we give it two iterators. So we give it the first one, which will be the width, second one, which will be the height. Call that indices, pass that to a list. So it will take space in memory, but we will need it. Go ahead and run that. It won't actually be doing anything because what it's doing is basically just redrawing this over and over again. What we need to do now is we need to tell it that every single pixel up to the current index needs to be changed to the filtered image. So that's quite easy. We can do im display of indices the frame. The indices now is a list of XY pairs, index X and index Y pairs, going from left to right, top to bottom. We can say that particular pixel now should be the filtered pixel. Go ahead and plot that, and this should now be working. Problem is that it's going to be very slow. You can see here it's doing something, but it's doing it in a very strange way. And the reason it was doing that is because I want to skip every certain amount of frames, because if we do it one pixel at a time, it's going to take forever to do any reasonable size image. So let's go ahead and be a bit smarter about this. So let's say I want the animation to last for 10 seconds, or at least 10 seconds, because it depends whether it can hit the FPS. So 10 seconds times 30 frames per second gives me a total frame number, 300, which you can write here. Okay, so total frames I want. I can then say I want to increment the number of frames on the plot. So we know that the total number of pixels on the plot is width times height. And we know that this list of indices gives you every single index for every single pixel. And so if we do the length of that, divided by our f total, so our total number of frames that we'll be plotting, pass that to an integer, that will now be an increment. And then in our frames, we say go from 0 to the total number of pixels in this increment. And then in our update function, all we have to do is make sure that we respect that. So we can go from the current frame, which is going up in the increment, going plus the increment, then we can get the x and y indices, which is now I, or indices of I, and then for every pixel in the display image, we can swap it with the pixel from the filtered image. When we go ahead and run that now, we see we get exactly what we want. So this should last around 10 seconds, assuming we're hitting the 30 FPS, which we're probably not. So it's probably going to be a bit slower, but we get exactly what we want. We've successfully applied the filter to the image in real time. And I think this looks pretty nice. It's showing you what it's doing. And the actual convolution itself, if you did it this way, so a lot of algorithms for the convolution will simply use the FFT, transform the kernel and the image into the FFT domain, and then multiply them together, and then transform back to the space domain. But if doing the actual convolution in the spatial domain, exactly what it does, it sweeps along, choosing a certain chunk of the image. I have another image as well, which should pose a bit of an interesting problem. So it's an A, but you see it's a bit blurry, so I've called it blurry A. It's a PNG. And that means that the data that we get will be between 0 and 1. Watch what happens when I plot this. Nothing. It gives me a really hard time now. And if we look, it comes from the problem here where we divided by 255. We don't want to do that. But we know that we've got a situation where when we have an alpha channel, we know that we don't go ahead and add an alpha channel. So why don't, in this RGB to RGB alpha function, we add this divide by 255 here. So if the image comes along and it has 4 channels already, so it's a PNG image with the RGB values between 0 and 1, we know that it's already between 0 and 1. Whereas if it's only got 3 channels and it's an RGB image, more than likely going to be between 0 and 255, so 8-bit per color channel. And so we can go ahead and just modify that. So now it works. So on the left we have our image, which is our blur area, and on the right we have our filter running over it, doing edge detection, and you see it successfully finds the edge. And if we swap back to our cat, we should see that nothing should have changed. We still see the cat on the left, and we should still be able to see the filter acting on the right. Let's try one more filter. Instead of edge detection, let's do sharpen. And you can also see how these filters could be applied sequentially, do one filter after the other, with the order actually mattering. And now look at the sharpening filter. See something really, really nice here. You can see that as the sharpening filter goes over, where this image was actually quite blurry, so quite soft, it's now massively enhancing those parts of the image. So you can really see on the cat's whiskers, and how the whiskers are a nice bright white colour and really stand out. And on things like the eyes, so the slit on the eye and the actual eyeball itself almost looks more vibrant. So I think that's really nice. It is complaining here about something, and that's because we might be exceeding the number I in these frames. So we can put a little guard in there, just saying that if the value I is greater than the length of the indices, then we just go ahead and break, so there's no more data to change. Again, let's just watch the cat, over the sharpening filter, going over the cat. Which looks really, really nice. Switch back to the blurry A photo image, and look what the sharpening filter is doing now. It's removing this blur around the shape, forming a nice crisp image on the right. So this would be good for reconstructing text, for example, from blur images. So I hope you found this interesting. We've seen how we can use 2 different filters on 2 different sorts of images, but more importantly, use Python to actually be able to plot the filtering in real time. We actually did cheat, so we prepared the filtered image using the SciPy library, which does it very, very quickly. It's got very well optimized C code behind the scenes to actually how it does the filtering. But then what we've done is basically displayed chunks of that coming through, which is actually what the definition of the convolution, which is applying the kernel to the image, is doing. It's a sum up all the points from the image, which is f. So go over for every point in the image, do the convolution, which is the summation of this weighting function times the pixels around the pixel of interest, and output that. So that's just the definition of convolution there. So you can imagine it doing this sweeping motion. And the advantage of using the built-in SciPy functions is that we don't have to go ahead and try and handle things like the edge cases. So when you're at the edge and your kernel can't actually extend past the image, what do you do? Do you mirror it? Do you wrap it? Etc, etc. So we avoided all that, and we just used the built-in fast code behind the scenes. So I hope you like this video. I think it's quite nice just to see how some of these filters work, and especially sharpening, because that happens quite a lot on photographs. You do often get a little bit of sharpening. Even things like OBS that streams tend to use some nice filters that involve sharpening the image, especially for upscaling. Now you will get some complaints down here. Minimize myself. And that's because the image show from the matplotlib only likes values between 0 and 1 for the RGB. But once filtered, you see we can get pixels that are not between 0 and 1. So some of them may dip below, some of them may dip above on some of the different RGB channels. In that case, it will simply clip those values. That's not a problem. If you do try and normalize it, say you normalize to the RGB sum, so the white value, what you end up with is quite a washed out image. Likewise, if you try to normalize every single individual channel, or normalize to the minimum of all the channels and normalize to the maximum of all the channels, again you get quite a washed out image. It's actually better to let some of these values clip outside and then let those be clipped off, because then that gives you a much nicer image like this. So for example, that white whisker there has been clipped, which which is fine because the rest of the image is then preserved in terms of its relative brightness and chroma. So thank you for watching. I believe this has been quite a nice video, just showing all the different filterings, just showing how a convolution filter works. So taking this small little kernel and applying it to an image using convolution and produce some quite nice results. Another thing to say is that these are actually very fast. So typically a convolution can be done in n log n time. So it's a rather fast operation. Which we see here, the most common fast convolution algorithms use the fast Fourier transform algorithm via the circular convolution theorem. So behind the scenes, these can be done very fast, often with a lot of hardware support.